Hello there, and welcome to Sleep Science, where the mysteries of the cosmos become gentle companions for your journey to rest. Tonight, we're drifting into one of the universe's most fascinating secrets: black holes. Those mysterious, invisible giants that lurk in the darkness between stars, bending space and time around them like cosmic whirlpools. Before we begin our quiet expedition, feel free to share where in the world you're listening from and what time it is. There's something wonderful about exploring the infinite while scattered across our own little planet's time zones. Now, black holes might sound intimidating, but don't worry. We'll take a gentle wander through their story together. We'll discover how they're born from the dreams of dying stars, how they twist the very fabric of reality, and why they're not quite the cosmic vacuum cleaners you might imagine. So settle in, take a slow breath, and let's begin our quiet voyage into the heart of darkness and light. Let's begin with something wonderfully paradoxical. Black holes aren't actually holes, and they're not exactly black either. They're among the most massive objects in the universe, yet they're completely invisible. They're regions of space where gravity has become so strong that nothing, not matter, not light, not even time itself, behaves quite the way you'd expect. Imagine, if you will, a place where the rules get quietly rewritten, where up and down lose their meaning, where clocks tick differently, and where the very fabric of space and time gets pulled and stretched like warm taffy. That's the neighborhood of a black hole, and it's both more extreme and more gentle than you might imagine. The term black hole itself is relatively new, coined in 1967 by physicist John Wheeler during a lecture. Before that, scientists called them frozen stars or dark stars, which honestly sounds much more poetic. But Wheeler's name stuck, perhaps because it captures something essential about these cosmic enigmas. They appear as holes in the starry sky, dark circles where light simply vanishes. But what exactly is a black hole? At its heart, it's a region where matter has collapsed down to a point of infinite density called a singularity, creating a gravitational field so intense that it warps the space around it beyond recognition. Think of space-time as a stretched rubber sheet. Place a marble on it, and it creates a small dip. Place a bowling ball, and the dip gets deeper. But a black hole, that's like dropping something so heavy that it tears right through the sheet, creating a funnel that leads, well, nobody quite knows where. The boundary around this cosmic funnel is called the event horizon, and it's perhaps the most important invisible line in the universe. Cross it, and you're committed to a one-way journey toward the center. It's not a physical surface you could touch or see, but rather a mathematical boundary where the escape velocity equals the speed of light. Since nothing can travel faster than light, nothing that crosses this line can ever return to tell us what lies beyond. This might sound terrifying, but here's something quietly astonishing. If you were falling toward a black hole, you wouldn't feel the moment you cross the event horizon. There'd be no dramatic border, no sudden change, no cosmic point of no return sign. To you, space would feel perfectly normal. It's only to an outside observer that you'd appear to slow down, redshift, and eventually fade from view, frozen forever at the edge of the event horizon, like a cosmic photograph. Black holes come in different sizes, and size matters quite a bit in their neighborhood. Stellar mass black holes, formed from collapsed stars, might have event horizons just a few kilometers across. But don't let their modest size fool you. They pack the mass of several suns into that tiny space. Then there are the supermassive black holes, lurking at the centers of galaxies with masses millions or billions of times greater than our Sun. Their event horizons could encompass entire solar systems. The physics of black holes touches on some of the deepest questions in science. They sit at the intersection of Einstein's general relativity and quantum mechanics, two theories that describe the universe beautifully, but seem to contradict each other when pushed to extremes. Black holes are those extremes made manifest, cosmic laboratories where the fundamental laws of physics get tested to their breaking point. What's particularly fascinating is how democratic black holes are in their appetites. They don't discriminate between matter and energy, between information and emptiness. Everything that ventures too close gets the same treatment. A slow spiral inward, getting stretched and heated until it crosses that invisible boundary and disappears from our universe. Or does it? That question, what happens to information that falls into a black hole, is one of the biggest puzzles in modern physics. There's something almost meditative about contemplating black holes. They're the universe's great simplifiers, reducing all the complexity of matter and energy to just a few basic properties: mass, electric charge, and spin. Everything else, the color of your shirt, the melody of your favorite song, the chemical composition of a distant planet, gets erased, or at least hidden beyond our ability to observe. Yet for all their reputation as cosmic destroyers, black holes are also creators. They shape galaxies, trigger star formation, and may even play a role in seeding new universes. They're not just endings, but beginnings. Not just destroyers, but architects of cosmic structure. And so we find ourselves contemplating these invisible giants, these tears in the fabric of reality, these cosmic enigmas that challenge everything we think we know about space, time, and existence itself. They remind us that the universe is far stranger and more wonderful than our everyday experience suggests. In the darkness between stars, gravity writes poetry that we're only just beginning to read. Not all stars get to enjoy a quiet retirement. While smaller stars like our Sun will eventually puff up, shed their outer layers, and settle into a peaceful existence as white dwarfs, cosmic embers cooling slowly over billions of years. The largest stars face a far more dramatic finale. Their story ends not with a gentle sigh, but with the most violent explosion the universe can produce, followed by a collapse so complete it tears a hole in reality itself. Let's take a gentle journey through the life of a massive star, one with at least 20 or 30 times the mass of our Sun. For most of its existence, this stellar giant lives in perfect balance. In its core, nuclear fusion burns hydrogen into helium, helium into carbon, carbon into heavier elements, each step releasing tremendous energy. This outward pressure from fusion holds the star up against its own crushing gravity, like an endless explosion contained within a gravitational embrace. But here's where the story takes a beautiful, inevitable turn toward darkness. Unlike smaller stars that can sustain this balance for tens of billions of years, massive stars burn through their fuel with reckless abandon. They're the cosmic equivalent of racing cars running on high octane. Brilliant, powerful, and destined for a short but spectacular existence. As the star ages, it begins building up layers like a giant onion. Hydrogen burns to helium in the outer shells, while deeper layers fuse heavier and heavier elements: carbon, oxygen, silicon. At the very center, iron begins to accumulate, and iron, in the nuclear world, is a dead end. It takes more energy to fuse iron into heavier elements than the process releases. The star's core engine sputters, falters, and finally stops. What happens next unfolds in seconds, though it's been building for millions of years. Without the outward pressure of fusion, gravity wins decisively. The core collapses catastrophically, shrinking from the size of Earth to perhaps 20 kilometers across in less time than it takes to blink. The density becomes unimaginable. A teaspoon of this material would weigh as much as a mountain. But the collapse doesn't stop there. If the star is massive enough, not even the pressure of neutrons packed together can halt gravity's relentless squeeze. The core continues shrinking, past the point where matter as we know it can exist, until all of the star's mass gets compressed into a point of infinite density, a singularity. The formation of this singularity is, in some ways, the universe's most elegant magic trick. Matter doesn't just disappear. It gets concentrated into something so small it has no size at all, yet so massive it warps space and time around itself. It's as if the star, in its final moment, decides to become pure gravity, distilled and concentrated into mathematical perfection. The outer layers of the star, meanwhile, experience the shockwave of the core's collapse. They rebound outward in a supernova explosion so bright it can outshine an entire galaxy for weeks. These explosions are visible across cosmic distances, announcing the birth of a black hole to anyone who cares to watch. It's the universe's way of saying, something extraordinary just happened here. But not every massive star becomes a black hole. There's a critical threshold, called the Chandrasekhar limit, after the Indian astrophysicist who first calculated it. Stars below about 25 solar masses might explode as supernovae, but leave behind neutron stars, incredibly dense objects where a sugar cube-sized piece would weigh as much as Mount Everest. Only the true giants cross the line into black hole territory. The transition from star to black hole isn't gradual, it's sudden and absolute. One moment you have a ball of gas and plasma following the familiar rules of stellar physics. The next, you have something that operates by entirely different principles, where the normal concepts of surface, temperature, and composition simply don't apply. There's something quietly poetic about this transformation. The star that once warmed planets and nurtured solar systems becomes something that can trap light itself. The nuclear furnace that created elements in its core, the carbon in your cells, the oxygen you breathe, the iron in your blood, becomes a region where even atoms cannot exist in their familiar form. And yet, this isn't really an ending but a transformation. The black hole carries with it the gravitational memory of the star that created it. Its mass remains, even as its matter disappears beyond the event horizon. In a sense, the star doesn't die. It simply changes its relationship with the rest of the universe, becoming a gravitational sculpture carved from the fabric of space-time itself. Some black holes are born alone, but others form in pairs or groups when multiple massive stars in a system undergo this transformation. These binary black holes can spiral around each other for millions of years, gradually drawing closer as they radiate away energy in the form of gravitational waves, ripples in space-time itself that we've only recently learned to detect. The universe is constantly creating new black holes through stellar collapse, though we rarely witness the moment of birth directly. Most supernovae occur in distant galaxies, appearing as brief new stars that brighten and then fade over weeks or months. But occasionally, we catch one in our own galactic neighborhood, and astronomers around the world turn their telescopes toward the dying light of a star, becoming something else entirely. So the next time you look up at the night sky, remember that some of those distant points of light are massive stars living on borrowed time, burning through their nuclear fuel at a pace that will inevitably lead them toward darkness. They're writing the final chapters of stellar stories that began with the gentle collapse of gas clouds and will end with the birth of black holes. It's the universe's way of recycling matter and energy, turning the ashes of dead stars into the seeds of cosmic mysteries. Here's something rather strange. The most important boundary in the universe is completely invisible and doesn't actually exist. The event horizon of a black hole is both the ultimate point of no return and, from the right perspective, just empty space. It's a line you can cross without knowing you've crossed it, yet once you do, you're permanently cut off from the rest of reality forever. The event horizon gets its name because it marks the boundary between events that can influence the outside universe and those that cannot. Cross this invisible line, and you become permanently cut off from the rest of reality. Your future becomes entirely contained within the black hole's embrace, unable to send any signal, any information, any influence back to the world you've left behind. It's the ultimate one-way membrane. But here's what makes it so wonderfully strange. The event horizon isn't a physical thing. You couldn't reach out and touch it, couldn't paint it red or hang a sign on it. It's a mathematical surface defined purely by geometry and gravity. Think of it as the surface of a sphere around the black hole, where the escape velocity equals the speed of light. Since nothing in the universe can travel faster than light, nothing can escape from within this boundary. The size of this boundary depends entirely on the black hole's mass. For a black hole with the mass of our Sun, the event horizon would have a radius of about 3 kilometers. That's remarkably small for something so massive. Imagine the entire Sun compressed down so that its gravitational reach only extends 3 kilometers from its center. A supermassive black hole with 1 billion solar masses, on the other hand, might have an event horizon larger than our solar system. Now, let's take a gentle thought experiment. Imagine you're an astronaut on an unfortunate trajectory toward a stellar mass black hole. As you fall inward, space begins to feel increasingly strange. The tidal forces, the difference in gravitational pull between your head and your feet, start to stretch you vertically and squeeze you horizontally. Physicists have given this process the rather undignified name spaghettification, though the cosmic taffy pull might be more poetic. But here's the curious thing. The strength of these tidal forces depends on the size of the black hole. For a small, stellar mass black hole, you'd be stretched to your limit well before reaching the event horizon. But for a supermassive black hole, the tidal forces near the event horizon are surprisingly gentle. You could cross that cosmic boundary intact, unaware that you've just passed the point of no return. To an outside observer watching your fall, something even stranger occurs. As you approach the event horizon, you appear to slow down dramatically. The light from your spacesuit becomes increasingly redshifted, shifting from white to red to infrared and beyond. You seem to freeze at the event horizon, your image growing fainter and redder until it fades from view entirely. To them, you never actually cross the boundary. You become a slowly fading photograph, eternally suspended at the edge of the black hole. But from your perspective, time flows normally. You pass through the event horizon in finite time, perhaps even unaware of the exact moment when you cross it. The stars above you begin to blue shift and compress into a bright ring, while the darkness below yawns ever wider. You've entered a region of space-time with very different rules. Inside the event horizon, the familiar relationship between space and time gets turned inside out. In our normal experience, you can move freely through space, but are carried inexorably forward through time. But within a black hole, you're carried inexorably inward through space, while your relationship with time becomes negotiable. The direction toward the center becomes as unavoidable as the future is in normal space-time. This leads to one of the most profound questions in physics. What happens to information that crosses the event horizon? If you fall into a black hole carrying a memory, a photograph, or the complete works of Shakespeare, that information seems to vanish from the universe forever. But quantum mechanics suggests that information cannot be destroyed, leading to what's known as the information paradox. Some physicists propose that the information somehow gets encoded on the event horizon itself, like a cosmic hologram. Others suggest it eventually escapes through Hawking radiation. The debate continues, and the black hole keeps its secrets. The event horizon also represents a profound asymmetry in the universe. From the outside, it appears as a surface of no return. But from the inside, it's simply empty space. Curved space, certainly, but space nonetheless. This dual nature reflects one of the deeper mysteries of black holes. They exist simultaneously as objects in our universe and as gateways to somewhere else. Some theories suggest that what we perceive as the interior of a black hole might be connected to other regions of space-time, possibly even other universes. These hypothetical connections, called wormholes, would make the event horizon not just a boundary, but a bridge. Of course, traveling through such a bridge would likely require surviving forces that would reduce any ordinary matter to its component particles, so it's not exactly a practical form of transportation. The study of event horizons has also led to surprising insights about the nature of reality itself. Stephen Hawking's work on black hole thermodynamics revealed that event horizons have temperature and entropy, properties we usually associate with matter, rather than empty space. This suggests that the event horizon somehow contains information about everything that has fallen into the black hole, encoded in a way we don't yet fully understand. Perhaps most remarkably, the mathematics of event horizons applies beyond black holes. Our entire observable universe has an event horizon, a cosmic boundary beyond which light hasn't had time to reach us since the Big Bang. And if the universe continues to expand at an accelerating rate, distant galaxies will eventually cross our cosmic event horizon, disappearing from view forever as they're carried away by the expansion of space itself. So the event horizon isn't just a feature of black holes. It's a fundamental concept in our understanding of space, time, and information. It represents the ultimate barrier, the place where our ability to know meets the universe's capacity to hide its secrets. And yet, for all its cosmic significance, crossing one would feel remarkably like falling through empty space, carried inexorably toward whatever lies at the heart of darkness. Einstein's most elegant insight was realizing that gravity isn't a force at all. It's geometry having a bad day. Massive objects don't pull on things, they simply exist, and space-time politely rearranges itself around them like a cosmic butler smoothing out wrinkles in reality. But black holes take this gentle reshaping and turn it into something approaching cosmic origami, folding space and time into impossible shapes that would make a mathematician weep with joy. Imagine, if you will, space-time as a vast, flexible trampoline stretched tight across the cosmos. Place a marble on it, and it barely makes a dent. Set down a bowling ball, and it creates a noticeable depression. But a black hole, that's like dropping something so dense that it doesn't just dent the trampoline. It creates a funnel so deep it seems to disappear into another dimension entirely. This warping of space-time has consequences that ripple outward from the black hole like cosmic reverberations. Light, which normally travels in perfectly straight lines through empty space, finds itself following the curves and bends that mass has carved into reality. Near a black hole, light rays can be bent into loops, spirals, and impossible geometries that would have given ancient astronomers nightmares. One of the most beautiful effects of this warping is gravitational lensing. A black hole can act like a cosmic magnifying glass, bending the light from objects behind it and creating multiple images, rings, or distorted arcs. It's as if the universe has developed a sense of artistic flair, using gravity as a paintbrush to create abstract masterpieces across the sky. Astronomers have learned to use this effect to study distant galaxies that would otherwise be too faint to observe, turning black holes into natural telescopes. But the warping affects more than just light. Time itself gets caught in gravity's embrace and stretched like cosmic taffy. The closer you get to a black hole, the slower time moves relative to the rest of the universe. This isn't science fiction or metaphor. It's a measurable, observable effect called gravitational time dilation. Near the event horizon of a stellar mass black hole, time crawls so slowly that what feels like a minute to you might correspond to hours, days, or even years passing in the outside universe. This temporal stretching creates some wonderfully strange scenarios. If you could somehow hover just outside the event horizon of a black hole and watch the universe beyond, you'd see cosmic history unfold in fast forward. Stars would be born, age, and die in what seemed like moments. Galaxies would evolve, collide, and reshape themselves in an accelerated dance of light and matter. You'd become a witness to the universe's future, watching eons pass while experiencing only hours. The warping of space near a black hole also creates regions where the normal rules of geometry stop making sense. Close to the event horizon, space becomes so curved that parallel lines converge, and the shortest distance between 2 points is no longer a straight line, but a swooping arc that follows the contours of gravitational curvature. It's like trying to navigate on a sphere when you're used to flat maps. The familiar rules simply don't apply. Perhaps most remarkably, the extreme curvature near a black hole can create closed time-like curves, paths through space-time that loop back on themselves temporally. In theory, you could follow such a curve and arrive at your own past, though the practical difficulties of surviving the journey, not to mention the paradoxes involved, make this more of a mathematical curiosity than a travel option. The warping also affects the very structure of empty space. Quantum mechanics tells us that even the vacuum is filled with fluctuations, pairs of particles that pop into existence, dance briefly, and then annihilate each other. Near a black hole, the extreme curvature of space-time can separate these particle pairs, preventing them from finding each other again. This leads to Hawking radiation, the process by which black holes slowly evaporate by creating real particles from the quantum foam of empty space. The mathematical description of this warping is breathtakingly elegant. Einstein's field equations relate the curvature of space-time to the energy and matter it contains. For a black hole, these equations produce the Schwarzschild metric, a formula that describes how space and time bend around a spherically symmetric mass. It's a piece of mathematics so beautiful that some physicists frame it on their office walls like poetry. But black holes don't just warp space and time. They can also drag space-time along with them as they rotate. This effect, called frame dragging, means that anything near a spinning black hole gets carried along like a leaf in a cosmic whirlpool. Even light gets twisted and pulled in the direction of the black hole's rotation. It's as if the black hole is stirring the universe itself like honey. The study of space-time warping around black holes has led to some of the most precise tests of Einstein's theory. When two black holes spiral into each other and merge, they create ripples in space-time itself, gravitational waves that propagate outward at the speed of light. These waves are incredibly faint by the time they reach Earth, stretching and compressing space by less than 1,000th the width of a proton. Yet we can now detect them, opening up an entirely new way of observing the universe. The warping of space-time around black holes also connects to some of the deepest questions in physics. The holographic principle suggests that all the information contained within a region of space can be encoded on its boundary, like a cosmic hologram. For black holes, this means that everything that falls past the event horizon might somehow be preserved in the warped space-time at the boundary itself. And so we find ourselves contemplating these cosmic architects of curvature, these sculptors of space and time. Black holes don't just exist within the universe. They reshape it, mold it, and bend it to their gravitational will. They remind us that space and time aren't the fixed, unchanging stage we imagine them to be, but rather dynamic, flexible aspects of reality that dance to the rhythm of mass and energy. In their presence, the universe itself becomes a work of art, painted in curves and spirals that stretch from the quantum scale to the cosmic horizon. At the center of every black hole sits the universe's greatest mathematical embarrassment, a place where all the elegant equations of physics throw up their hands and start producing infinities like a cosmic calculator having a nervous breakdown. The singularity is where everything we think we know about reality goes to hide, leaving behind only question marks and the uneasy feeling that the universe might be playing an elaborate joke on us. The journey toward this mysterious heart begins the moment you cross the event horizon. Unlike the gentle passage through that invisible boundary, your approach to the singularity becomes increasingly dramatic. The tidal forces that stretch you grow stronger with each kilometer, pulling at your atoms with an intensity that eventually overcomes even the strongest chemical bonds. Long before you reach the center, you'd be reduced to a stream of elementary particles, joining the cosmic parade of matter that has made this one-way journey before you. But what exactly is a singularity? In the mathematics of general relativity, it appears as a place where the curvature of space-time becomes infinite, a point where Einstein's elegant equations begin producing meaningless results like infinity and undefined. It's where our most successful theory of gravity throws up its hands and admits defeat. The singularity represents the edge of our current understanding, a mathematical cliff beyond which we cannot see. There are actually different types of singularities predicted by the mathematics. The simplest is the Schwarzschild singularity, found at the center of a non-rotating black hole. Here, all of the black hole's mass is theoretically concentrated into a point of zero size. But real black holes usually spin, and spinning black holes contain something even stranger: a ring singularity. Instead of a point, the mass collapses into an infinitely thin ring, creating a donut-shaped region where the laws of physics go haywire. The ring singularity of a rotating black hole, called a Kerr black hole after mathematician Roy Kerr, who first described it, opens up possibilities that sound more like science fiction than science fact. The mathematics suggests that you might be able to pass through the ring without actually hitting the singularity, potentially emerging into a mirror universe with opposite physical laws. Of course, the journey would likely be fatal in ways that make ordinary death seem mundane, so it's not exactly a practical exploration strategy. But here's where the story takes an intriguing turn. Many physicists suspect that these mathematical singularities don't actually exist in nature. They're artifacts of our incomplete understanding, places where general relativity, which works beautifully at large scales, meets quantum mechanics, which governs the microscopic world. Just as classical physics breaks down at the atomic scale and gives way to quantum mechanics, perhaps general relativity breaks down at the scale of the singularity and gives way to something new. One possibility is that quantum effects prevent the formation of true singularities. At incredibly small scales, quantum uncertainty makes the very concept of a precise point meaningless. Perhaps what we call a singularity is actually a quantum fuzzball, a region of space so small and dense that it exists in a quantum superposition of states. Or maybe it's a place where space and time themselves become discretized, made up of tiny, indivisible units like cosmic pixels. Another intriguing possibility comes from string theory, which suggests that what we perceive as a singularity might actually be a highly curved but finite region of higher dimensional space. In this view, the singularity is like a cosmic optical illusion. It appears infinite from our limited three-dimensional perspective, but it's actually just a place where extra dimensions are curled up so tightly that we can't perceive them. Some theories propose that the center of a black hole might contain something called a Planck star, an object so dense that quantum pressure balances gravitational collapse, creating a kind of quantum bounce. In this scenario, the matter falling into the black hole doesn't collapse to infinite density, but instead gets compressed to the highest density that quantum mechanics allows before rebounding outward. The catch is that this rebound would take place so slowly, due to time dilation, that from the outside universe's perspective, it would never actually occur. Even more exotic proposals suggest that black hole interiors might be connected to other regions of spacetime through Einstein-Rosen bridges or wormholes. These hypothetical tunnels could potentially link different parts of our universe, or even connect to entirely different universes. The singularity, in this view, might be the entrance to a cosmic subway system, though one with decidedly inhospitable travel conditions. The mystery of the singularity is intimately connected to one of the biggest problems in physics: the unification of general relativity and quantum mechanics. These two theories describe the universe magnificently within their respective domains, but they seem fundamentally incompatible when forced to coexist. The singularity is where this incompatibility becomes most acute, where the smooth curves of Einstein's spacetime meet the quantum fuzziness of Heisenberg's uncertainty principle. Resolving this conflict may require a complete revolution in our understanding of space, time, and matter. Some physicists believe the answer lies in theories of quantum gravity, such as loop quantum gravity or string theory. Others propose that the very concepts of space and time might be emergent properties of something more fundamental, like quantum entanglement or information processing. The information paradox adds another layer to the mystery. If information that falls into a black hole is destroyed at the singularity, it would violate one of the fundamental principles of quantum mechanics. But if the information somehow survives, where does it go? Some theories suggest it gets encoded on the event horizon itself, while others propose it escapes through correlations in Hawking radiation. Perhaps most remarkably, the study of singularities has revealed deep connections between black holes, thermodynamics, and information theory. The holographic principle suggests that all the information in a volume of space can be encoded on its boundary, like a cosmic hologram. For black holes, this implies that the three-dimensional interior might be a projection of information stored on the two-dimensional event horizon. And so we find ourselves contemplating these ultimate mysteries, these places where mathematics meets its limits and reality reveals its deepest secrets. The singularity reminds us that for all our scientific progress, there are still fundamental questions about the nature of existence that remain unanswered. It's a cosmic koan, a riddle wrapped in an enigma, hiding at the heart of some of the universe's most exotic objects. Whether singularities actually exist in nature or are simply artifacts of our incomplete theories, they serve as powerful reminders of the universe's capacity for surprise. They mark the boundaries of our current knowledge and point the way toward new discoveries that may revolutionize our understanding of reality itself. In the end, perhaps the greatest mystery isn't what lies at the center of a black hole, but what that mystery teaches us about the fundamental nature of existence. Here's perhaps the most quietly astonishing discovery about black holes. These cosmic giants that swallow everything, including light itself, are actually evaporating, very, very slowly, like cosmic puddles drying in an impossibly patient sun. Stephen Hawking realized that black holes aren't perfectly black after all. They glow with a faint radiation so subtle it makes candlelight look like a supernova. And this gentle glow is slowly carrying them away, particle by particle, until even the mightiest black hole becomes nothing more than a whisper of quantum foam. The story begins with quantum mechanics and its delightful insistence that empty space isn't really empty. Even in the perfect vacuum between stars, pairs of particles constantly pop into existence, dance briefly with each other, and then annihilate back into nothingness. It's like the universe is having a continuous microscopic celebration that we can barely detect. These virtual particles appear everywhere, all the time, borrowing a little energy from the quantum field with the promise to pay it back almost instantly. But near a black hole's event horizon, something wonderful and strange happens to these particle pairs. The intense gravitational field can sometimes separate them before they have a chance to find each other again. One particle falls past the event horizon, while its partner escapes into space. From the outside universe's perspective, a real particle has just been created from nothing, but the black hole has paid the energy cost by losing a tiny bit of its own mass. This process, called Hawking radiation, means that black holes have a temperature. Not a temperature you could feel with your hand. It's incredibly cold, far colder than the cosmic microwave background that bathes the universe. A black hole with the mass of our Sun would have a temperature of about 60 billionths of a degree above absolute zero. That's so cold, it makes interstellar space feel tropical by comparison. Here's where the story takes a beautifully ironic turn. The smaller a black hole gets, the hotter it becomes. As it evaporates and loses mass, its temperature rises, causing it to evaporate faster, which makes it smaller and hotter still. It's a runaway process that ends with the black hole essentially exploding in a final burst of energy. Though exploding might be too dramatic a word for something that takes longer than the current age of the universe multiplied by trillions of trillions. The timescales involved are so vast they make geological time look like a coffee break. A black hole with the mass of our Sun would take approximately 10,067 years to evaporate completely. To put that in perspective, the universe is currently only about 14 billion years old, or 1.4 as 10 years. By the time stellar mass black holes finish evaporating, the universe will be unimaginably old and cold, populated only by elementary particles drifting apart in the darkness. But the process isn't uniform. The radiation doesn't emerge at a steady rate like steam from a kettle. Instead, it's random and chaotic, with particles appearing unpredictably around the event horizon. From the black hole's perspective, if black holes have perspectives, it's as if the vacuum around it keeps spontaneously creating matter and energy, slowly draining away its gravitational strength. This raises one of the most profound puzzles in modern physics, the information paradox. If information that falls into a black hole gets destroyed when the black hole evaporates, that would violate one of the fundamental principles of quantum mechanics. But if the information somehow escapes in the Hawking radiation, how does it get out? The radiation appears to be random and thermal, carrying no information about what fell in. It's like watching a library burn down and trying to reconstruct the books from the smoke. Some physicists propose that the information is preserved in correlations between the outgoing radiation, subtle quantum entanglements that encode everything that ever fell into the black hole. Others suggest that information isn't destroyed but gets transferred to a baby universe that buds off from the black hole's interior. Still others think the whole concept of information destruction might be the real problem, requiring us to rethink what information actually means. The discovery of Hawking radiation also revealed that black holes obey the laws of thermodynamics, just like ordinary objects. They have entropy proportional to the area of their event horizon, not their volume. This suggests that the information content of a black hole is somehow encoded on its surface, like a cosmic hologram. It's as if the three-dimensional interior is just a projection of information stored on the two-dimensional boundary. For supermassive black holes, the ones lurking at the centers of galaxies, the evaporation process is so slow it's barely theoretical. They're actually growing, absorbing more matter and energy from their surroundings than they lose to Hawking radiation. But in the far future, when star formation has ended and the universe has expanded and cooled, even these giants will begin their long, slow fade into quantum oblivion. There's something oddly comforting about the idea that even black holes, these seemingly permanent features of the cosmic landscape, are temporary. They're born, they live, and they die, just like stars and planets and people. The universe, it seems, has a way of recycling everything eventually. breaking down even the most exotic objects into their fundamental components. And so these cosmic vacuum cleaners, these devourers of light and matter, turn out to be surprisingly mortal. They glow with the faintest possible light, whisper the most subtle radiation, and slowly, gently give themselves back to the universe that created them. In the end, even darkness learns to shine. Every galaxy has a secret at its heart, a supermassive black hole that's been quietly orchestrating the cosmic dance for billions of years. These aren't the stellar corpses we've been discussing, but something far more ancient and mysterious. Black holes with masses millions or billions of times greater than our Sun, sitting at galactic centers like silent conductors, directing symphonies of stars. And here's the beautiful puzzle. We're not entirely sure how they got there, because they seem to have existed almost since the beginning of time itself. The discovery that galaxies harbor these central monsters was one of astronomy's most surprising revelations. For decades, astronomers had noticed that something massive and invisible lurked at the center of the Milky Way. But it wasn't until the 1990s that careful observations of stars orbiting this dark object confirmed what many had suspected. Our galaxy is built around a supermassive black hole called Sagittarius A, pronounced A star, weighing in at about 4 million solar masses. But Sagittarius A is practically a lightweight compared to some of the cosmic giants we've discovered. The black hole at the center of the galaxy M87, which became the first black hole ever photographed, has a mass of about 6.5 billion suns. That's so massive that its event horizon could swallow our entire solar system with room to spare. And even that's not the record holder. We've found supermassive black holes with masses exceeding 20 billion solar masses. Objects so large they stretch the imagination. What makes these giants particularly puzzling is not just their size, but their age. We've discovered supermassive black holes in galaxies so distant that we're seeing them as they were less than 1 billion years after the Big Bang. That should be impossible according to our understanding of how black holes grow. Starting from a stellar mass black hole and feeding at the maximum possible rate, it should take much longer than 1 billion years to reach supermassive proportions. This timing problem has led astronomers to propose exotic scenarios for supermassive black hole formation. Perhaps they began not as collapsed stars, but as direct collapsed black holes, massive gas clouds that skip the star formation phase entirely and collapse straight into black holes. Or maybe they formed from the first generation of stars, which might have been hundreds of times more massive than anything we see today, leaving behind black holes that were already impressively large. The relationship between supermassive black holes and their host galaxies is one of the most beautiful examples of cosmic symbiosis. The mass of a galaxy's central black hole is tightly correlated with the mass of the galaxy's central bulge of stars. This suggests that the black hole and the galaxy grew together, each influencing the other's development through a delicate cosmic dance that played out over billions of years. When supermassive black holes feed, they become some of the most luminous objects in the universe. As matter spirals into the black hole, it forms an accretion disk that heats up to millions of degrees, glowing brighter than entire galaxies. These active galactic nuclei can be seen across cosmic distances, serving as lighthouses that help us map the structure of the early universe. Some shoot jets of particles and energy thousands of light years into space, like cosmic searchlights sweeping across the darkness. But most of the time, including right now in our own galaxy, these supermassive black holes are remarkably quiet. Sagittarius A is currently on a starvation diet, consuming only about 1 Earth mass worth of material every million years or so. It glows faintly in radio waves and X-rays, but it's nothing like the brilliant quasars we see in distant galaxies. It's as if the galaxy's central engine is idling, waiting for its next meal. The gravitational influence of supermassive black holes extends far beyond their immediate vicinity. They help regulate star formation in the galactic center, create the orbital structure that maintains spiral arms, and may even play a role in dispersing the heavy elements created by dying stars throughout the galaxy. In a very real sense, the supermassive black hole is the heart of the galaxy, pumping energy and structure through the cosmic body around it. Future observations promise to reveal even more about these galactic giants. The Event Horizon Telescope, which captured the first image of M87's black hole, is working to image our own Sagittarius A. Space-based gravitational wave detectors will eventually be able to hear the collisions of supermassive black holes, events so violent they shake the fabric of space-time across the universe. Perhaps most intriguingly, supermassive black holes may hold clues to the ultimate fate of the universe. As galaxies merge over cosmic time, their central black holes will eventually merge as well, creating even more massive objects. In the far future, these merged supermassive black holes may be among the last surviving objects in a cold, dark universe, slowly evaporating through Hawking radiation until nothing remains but elementary particles and empty space. There's something profound about realizing that we live in a galaxy organized around a supermassive black hole. Every star in our cosmic neighborhood, including our Sun, follows an orbit ultimately determined by the gravitational pull of this invisible giant. We are, in a very real sense, inhabitants of a black hole's gravitational domain, participants in a cosmic ballet choreographed by one of the universe's most exotic objects. And yet, despite their enormous influence, these supermassive black holes remain surprisingly mysterious. We can measure their masses, track their effects on surrounding matter, and even photograph their shadows, but their origins and their ultimate destiny remain open questions. They remind us that even at the centers of the most familiar structures in the universe, our own galaxy included, mystery and wonder continue to dwell. How do you photograph something that's completely black against the darkness of space? It's like trying to take a picture of a shadow at midnight, except the shadow is millions of miles across and sitting 26,000 light years away. Yet in 2019, scientists did exactly that, capturing the first image of a black hole's event horizon and turning one of the universe's most elusive objects into something you could actually see on your phone screen. The challenge of detecting black holes has always been fundamental. They don't emit light, they don't reflect radiation, and they're essentially invisible holes cut out of the starry sky. For decades, astronomers had to play cosmic detective, looking for the gravitational fingerprints that black holes leave on their surroundings. It's like deducing the presence of an invisible dancer by watching how their partner moves across the floor. The first hints came from X-ray astronomy in the 1960s and 70s. Astronomers discovered intensely bright X-ray sources that flickered and varied in ways that suggested something massive and compact was involved. The X-rays weren't coming from the black holes themselves, but from the superheated material spiraling into them. As gas falls toward a black hole, it speeds up and heats up, eventually reaching temperatures of millions of degrees and glowing brilliantly in X-rays before disappearing forever, past the event horizon. One of the most convincing early pieces of evidence came from a system called Cygnus X1, where a normal star appeared to be orbiting an invisible companion that was far too massive to be a neutron star. By measuring the orbital motion of the visible star, astronomers could calculate the mass of its dark partner. When that mass exceeded the theoretical limit for neutron stars, the conclusion became inescapable. They were looking at a black hole. But indirect evidence, however compelling, wasn't the same as actually seeing a black hole. The breakthrough came with the development of very long baseline interferometry, a technique that links radio telescopes around the world to create a virtual telescope the size of Earth itself. The Event Horizon Telescope, EHT, uses this technique to achieve the incredible resolution needed to image the event horizon of a black hole. The first target was M87, the supermassive black hole at the center of the elliptical galaxy M87. At 6.5 billion solar masses and located 55 million light-years away, it presented the largest apparent size of any black hole in the sky, making it the most feasible target for the first attempt. Even so, imaging it required precision equivalent to reading the date on a coin on the surface of the moon. What the EHT actually captured wasn't the black hole itself, but its shadow, a dark silhouette against the bright accretion disk surrounding it. The image showed a ring of glowing matter with a dark center, exactly as Einstein's general relativity predicted. It was a triumph of both theoretical physics and observational astronomy, confirming that our mathematical understanding of these extreme objects matches reality. The process of creating that image was almost as remarkable as the result. Radio telescopes in Hawaii, Arizona, Spain, Chile, Mexico, and the South Pole all simultaneously observed M87 for several days in April 2017. The data from each telescope was recorded on specialized hard drives and shipped to correlation centers where supercomputers combined the signals to reconstruct the image. It took 2 years of data processing to produce the final photograph that made headlines around the world. But radio telescopes aren't the only way to hunt for black holes. Gravitational wave detectors like LIGO and Virgo have opened up an entirely new method of black hole astronomy. When two black holes spiral into each other and merge, they create ripples in space-time itself that propagate outward at the speed of light. These gravitational waves are incredibly faint by the time they reach Earth, but they carry detailed information about the black holes that created them. The first detection of gravitational waves in 2015 came from two black holes, each about 30 times the mass of the Sun, colliding 1.3 billion years ago. The signal lasted only a fraction of a second, but it told astronomers the masses of the black holes, how fast they were spinning, and how far away the collision occurred. It was like hearing the universe's own percussion section for the first time. Space-based observatories have also revealed black holes through their gravitational effects. The Hubble Space Telescope has measured the orbital motions of stars and gas clouds around suspected black holes, providing mass measurements accurate enough to confirm their black hole nature. The Chandra X-ray Observatory has captured spectacular images of jets and accretion disks around black holes, showing the complex interplay between matter, energy, and extreme gravity. Perhaps most remarkably, astronomers have begun tracking individual stars as they orbit the supermassive black hole at the center of our own galaxy. Using adaptive optics to correct for atmospheric turbulence, telescopes can follow these stars for decades, watching them speed up as they approach the black hole and slow down as they move away. One star, designated S2, passes so close to Sagittarius A that it reaches speeds of up to 7,650 kilometers per second, more than 2.5% the speed of light. The hunt for black holes has also revealed surprising diversity in these objects. We've discovered intermediate mass black holes with masses between stellar and supermassive varieties, though they remain relatively rare and mysterious. We found black holes spinning at nearly the maximum theoretical rate, as well as others that barely rotate at all. Some are actively feeding and blazing with energy, while others sit quietly in the cosmic dark. Each new detection method has revealed different aspects of black hole physics and behavior. X-ray observations show us the violence of accretion. Gravitational waves reveal the dynamics of mergers, and direct imaging lets us see the geometry of space-time itself. Together, these techniques are building a comprehensive picture of black holes as complex, dynamic objects that play crucial roles in cosmic evolution. The next frontier involves combining multiple detection methods simultaneously. Astronomers are working to coordinate gravitational wave detections with optical, X-ray, and radio observations to catch black hole mergers in the act across the electromagnetic spectrum. Future space missions will extend our black hole hunting capabilities even further. With improved resolution and sensitivity that will reveal even more of these cosmic mysteries. And so, through ingenuity, persistence, and increasingly sophisticated technology, we've learned to see the unseeable, to photograph shadows, and to hear the whispers of space-time itself. Black holes, once purely theoretical objects, have become observational realities that we can study, measure, and even watch as they evolve over time. The invisible has become visible, and the silent has found its voice in the gravitational waves that ripple through the cosmos. Time near a black hole develops a peculiar sense of rhythm, stretching and slowing like a cosmic waltz played at half speed. What feels perfectly normal to you, the steady beat of your heart, the measured pace of your breathing, becomes languorously slow to anyone watching from a safe distance. You could wave at a friend far away, and from their perspective your gesture might take hours, days, or even years to complete. Time, it turns out, is far more personal and negotiable than we ever imagined. This temporal choreography stems from one of Einstein's most profound insights. Gravity and acceleration are fundamentally the same thing, and both have the power to warp time itself. Just as time slows down when you travel at high speeds, it also slows down in strong gravitational fields. The closer you get to a massive object, the more slowly time passes relative to someone farther away. Near a black hole, where gravity reaches its most extreme expression, this effect becomes dramatically pronounced. Imagine you're an astronaut unfortunate enough to fall toward a black hole, while your colleague watches through a telescope from a spacecraft hovering safely in the distance. As you approach the event horizon, something remarkable happens to the relationship between your two experiences of time. From your perspective, your watch ticks normally, your thoughts flow at their usual pace, and nothing feels amiss. But to your colleague, your movements begin to slow down, as if you're gradually being transformed into a cosmic statue, The effect becomes more pronounced the closer you get to the event horizon. What feels like minutes to you might appear as hours to your distant observer. Eventually, as you approach that invisible boundary, you seem to freeze almost completely from their perspective. The light from your spacesuit becomes increasingly redshifted, fading from white to red to infrared and beyond, until you appear to fade away entirely. To the outside universe, you become a slowly dimming photograph, eternally suspended at the edge of the black hole. But here's where the story becomes beautifully strange. From your point of view, none of this happens. You pass through the event horizon in finite time, completely unaware of the temporal drama playing out for your observer. To you, the distant universe doesn't slow down, but instead begins to speed up dramatically. You might see stars evolving, galaxies colliding, and the future history of the cosmos unfolding in fast forward above you. This time, dilation isn't just theoretical. It's measurable, even in much weaker gravitational fields. GPS satellites orbiting Earth experience time slightly faster than we do on the surface, about 38 microseconds per day. That might not sound like much, but without constant corrections for this relativistic effect, GPS would be off by several kilometers within a single day. Your phone's navigation works only because Einstein's century-old insights about time and gravity are continuously factored into the calculations. The mathematics of time dilation follows a beautifully simple relationship. The stronger the gravitational field, the slower time moves. At the event horizon of a black hole, time dilation becomes infinite from an outside perspective. This creates a curious paradox. The outside universe never actually sees anything cross the event horizon. From the external viewpoint, matter accumulates at the boundary, getting redder and fainter, but never quite disappearing. This temporal stretching also affects the black hole's own evolution. From the perspective of someone falling in, the black hole appears static and unchanging. But from the outside, the black hole is constantly evolving, growing through accretion, potentially merging with other black holes, and even slowly evaporating through Hawking radiation. These two descriptions, static and dynamic, are both correct within their respective frames of reference. The phenomenon creates some delightfully mind-bending scenarios. If you could somehow hover just outside the event horizon of a supermassive black hole, which would require impossible amounts of energy, you could watch the entire future of the universe unfold. You'd see the sun expand into a red giant and eventually fade to a white dwarf. You'd witness galaxies merging, stars burning out, and eventually the cosmos itself growing cold and dark. All of this cosmic history would unfold in what feels like a reasonable amount of time to you, though billions of years would be passing in the outside universe. Rotating black holes add another layer of complexity to temporal effects. The spinning mass drags space-time around with it, creating what physicists call frame dragging. This means that even space itself gets pulled along in the direction of rotation, like honey being stirred with a spoon. In this twisted space-time, the concepts of forward and backward in time can become ambiguous, leading to closed time-like curves where, theoretically, cause and effect could form loops. The study of time near black holes has also revealed deep connections between gravity, quantum mechanics, and information theory. The holographic principle suggests that all the information in a region of space can be encoded on its boundary, much like a hologram encodes three-dimensional information on a two-dimensional surface. For black holes, This implies that everything that falls past the event horizon might somehow be preserved in the warped space-time at the boundary. Recent work on the black hole information paradox has led to even stranger proposals about the nature of time near event horizons. Some theories suggest that the interior of a black hole might be connected to its own past through quantum entanglement, creating a kind of temporal loop where the black hole's own evaporation in the far future influences its interior structure in the present. Time dilation near black holes also plays a crucial role in their eventual fate. As black holes evaporate through Hawking radiation, the process appears to accelerate from an outside perspective. The final moments of a black hole's life, when it releases its remaining energy in a burst of radiation, would seem to happen very quickly to distant observers, even though the total evaporation process takes an unimaginably long time. Perhaps most remarkably, the extreme time dilation near black holes offers a window into the fundamental nature of time itself. It reveals that our intuitive understanding of time as universal and absolute is merely an approximation that works in weak gravitational fields. Near black holes, time becomes fluid, personal, and deeply interconnected with the geometry of space itself. And so we find ourselves contemplating these cosmic clocks, these places where time learns new steps and dances to rhythms we're only beginning to understand. They remind us that time isn't the steady metronome we imagine it to be, but rather a flexible dimension that bends and flows with the mass and energy around it. In their presence, minutes can become hours, hours can become centuries, and the familiar progression of cause and effect can spiral into beautiful, impossible loops that challenge our most basic assumptions about reality. In the unimaginably distant future, when the last star has burned out and the universe has become a cold, dark expanse populated only by black holes and elementary particles, these gravitational giants will stage the final act of cosmic history. They'll sit in the darkness like ancient monuments, slowly giving themselves back to the quantum vacuum through the most patient process in the universe: evaporation by Hawking radiation. It's a goodbye so long and gradual it makes geological time look like a brief intermission. To understand just how leisurely this cosmic farewell is, consider that a black hole with the mass of our Sun would take approximately 10,067 years to completely evaporate. That's a number so large it defies comprehension. A 1 followed by 67 zeros. To put it in perspective, the current age of the universe is only about 14 billion years, or roughly 10 years. The time required for stellar mass black holes to evaporate is longer than the current age of the universe. By a factor of 10, quintillion, 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 quintillion. It's a timescale that makes eternity seem like a weekend getaway. And that's for the relatively small black holes. The supermassive giants at the centers of galaxies will take even longer to fade away. A black hole with 1 billion solar masses, typical of those found at galactic centers, would require about 10,990 years to evaporate completely. By this time, the universe will be so old and expanded that the cosmic microwave background radiation will have cooled to nearly absolute zero, and the very protons that make up ordinary matter may have begun to decay. The evaporation process itself is beautifully ironic. As a black hole loses mass through Hawking radiation, it actually gets hotter and begins to evaporate faster. It's a runaway process that starts glacially slow and ends in a final burst of energy. For most of a black hole's lifetime, The evaporation is so gradual as to be essentially imperceptible. But in the last few moments, and we're talking about moments relative to the overall timescale, the black hole effectively explodes, releasing its remaining mass as pure energy. During this impossibly distant era, black holes will be among the only remaining sources of energy in the universe. Everything else will have succumbed to entropy. Stars will have exhausted their nuclear fuel. Planets will have been consumed or ejected from their dying solar systems. And even the largest structures in the universe will have been torn apart by the accelerating expansion of space. In this cold, dark cosmos, the faint glow of Hawking radiation from evaporating black holes will provide the universe's last warmth. But even this final phase of cosmic history has its own peculiar beauty. As black holes evaporate, they'll create brief, localized regions of energy and complexity in an otherwise dead universe. The particles emerging from Hawking radiation will form temporary clouds of matter that might, just might, organize themselves into patterns reminiscent of the complexity we see today. It's possible that even in this distant future, the universe might find ways to surprise itself. The very final moments of a black hole's existence are particularly intriguing. In the last second of its trillion year lifetime, a stellar mass black hole would release energy equivalent to millions of hydrogen bombs. This final flash would briefly illuminate a tiny corner of the otherwise dark universe, like a cosmic candle flickering out after an impossibly long burn. What happens to the information that fell into these black holes over their vast lifetimes remains one of physics' greatest mysteries. If information is truly conserved, as quantum mechanics suggests, then somehow the complete history of everything that ever fell into the black hole, every star, every planet, every photograph, every love letter, must be encoded in the seemingly random Hawking radiation. It's as if the universe maintains a perfect memory, even as everything else fades away. Some theories propose that the information emerges gradually throughout the evaporation process, encoded in subtle correlations between particles of Hawking radiation. Others suggest that it all comes out in the final burst, compressed into a form we don't yet understand. Still others propose that the information never really entered the black hole at all, but was somehow captured and stored at the event horizon, waiting patiently for the black hole to evaporate and release it back to the universe. The death of the last black hole will mark what cosmologists call the end of the stelliferous era and the beginning of the black hole era, followed eventually by the dark era. In this final epoch, the universe will consist mainly of elementary particles, electrons, positrons, neutrinos, and photons, drifting apart as space continues to expand. The temperature will approach absolute zero, and the rate of interesting events will slow to almost nothing. Yet even this isn't necessarily the end of the story. Some theories suggest that quantum fluctuations in this cold, empty universe might occasionally produce new structures, new complexities, even new universes. The timescales involved would be unimaginably vast, periods compared to which the lifetime of black holes seems brief. But in an infinite universe with infinite time, even the most improbable events become inevitable. There's something profoundly moving about contemplating this cosmic endgame. The black holes that seem so permanent and indestructible from our perspective are actually temporary features of an evolving universe. They're born from dying stars, live for eons beyond our comprehension, and eventually give themselves back to the quantum vacuum from which they emerged. They're not endings, but transitions. Not destroyers, but recyclers of cosmic energy and information. The study of black hole evaporation has also led to some of the deepest insights in theoretical physics. The connection between gravity, thermodynamics, and information theory that emerges from Hawking's work suggests that these seemingly disparate fields of physics are fundamentally unified. Black holes, in their slow dissolution, are teaching us about the basic structure of reality itself. In the end, the universe that gave birth to black holes will also witness their peaceful departure. They'll fade away like cosmic embers cooling in the dark, their final whispers of Hawking radiation carrying with them the memory of everything they've witnessed: the formation of galaxies, the birth and death of countless stars, the rise and fall of civilizations we can only imagine. They're the universe's longest-lived storytellers, and their evaporation marks the closing of the final chapter in the book of cosmic history. And so, in contemplating these gravitational giants and their ultimate fate, we're reminded that even the most permanent-seeming features of our universe are temporary. Everything that has a beginning has an ending, even black holes. But in their incredibly long lives and patient deaths, they embody something beautiful about the cosmos: its ability to create structure and complexity, to preserve information and memory, and to transform endings into new beginnings across timescales that humble our human perspective and inspire our cosmic imagination. And so, friend, we arrive at the end of our gentle voyage into the heart of cosmic darkness, though perhaps darkness isn't quite the right word anymore. We've discovered that black holes aren't really holes, that they glow with the faintest possible light, and that they're not eternal destroyers but temporary sculptors of space-time, slowly giving themselves back to the universe that created them. We followed their story from the dramatic collapse of dying stars to the patient evaporation that will mark the final chapter of cosmic history. We've seen them bend space and time like cosmic artists, reveal the fluid nature of reality itself, and challenge everything we thought we knew about the fundamental laws of physics. Along the way, we've learned that the universe is far stranger, more beautiful, and more interconnected than our everyday experience suggests. Perhaps tonight, as you settle into sleep, you'll carry with you a sense of wonder for these invisible giants that lurk between the stars. They remind us that even in the darkest corners of the cosmos, extraordinary things are happening. Matter dancing on the edge of forever, time itself learning new rhythms, and the universe writing poetry in the language of gravity and light. If this quiet expedition brought you any peace, any sense of cosmic connection, or simply helped your thoughts drift gently toward dreams, we'd be honored if you joined us for future journeys through the mysteries of science. Sleep well, fellow traveler, and may your dreams be as boundless as the space between stars. Thanks for joining us here at Sleep Science.